Welcome back to this course on condensed matter physics and topology. So, we were discussing the Schuh-Schrieffer-Heger model, which is a simple paradigmatic model for topological consideration. That is, it has a non-trivial phase, which we call it as a topological phase, and this happens by tuning the parameters of the Hamiltonian. That is, if you tune the intercell and the intracell hopping in a certain way, when the intercell hopping becomes larger than the intracell hopping, then the system enters into a topological phase, and the topological phase is shown via calculation of the winding number, which is closed curve in the dx dy plane, and it encloses the origin. And the trivial phase, which is non-topological, is also a gapped phase, but however, this closed curve that we had just talked about in the dx dy plane does not enclose the origin. Okay. So, just to give you the preliminaries of that, so we have written down the Schuh-Schrieffer-Heger or the SSH Hamiltonian in momentum space, and it has this form here. So, it has this form where these it has an off diagonal form, and these f of k is of course these t1 plus t2 e to the power minus I k, where k varies from minus pi to plus pi. That is the Brillouin zone for one dimensional system. So, this allowed us to write down the Hamiltonian in the form of a massless Dirac Hamiltonian, which we have discussed. It is a d dot sigma, and we have also said that a possible realization would be this polyacetylene chain, which consists of single bond and double bond of carbon atoms. Each of the carbon atoms are connected to a hydrogen atom, but the hydrogen atom is not important in this. So, it is a carbon atom, and carbon has one electron available for conduction per atom, and so we should get a tight binding Hamiltonian corresponding to this, and this is the tight binding Hamiltonian, where H alpha beta is has a form which is a massless Dirac form. Sigmas are the Pauli matrices sigma x, sigma y, and sigma z. So, the important information about topology is encoded in this d vector, and it is very important to note that this dz is equal to 0, okay, for all k. So, for all values of k, dz is equal to 0, which means that the spectrum is gapped always, and if the dx and dy, which are non-zero, so dx and dy, in this plane it is possible to draw, or rather plot a closed curve by varying k in the region minus pi to plus pi, or within the range minus pi to plus pi, and this will determine whether there is a trivial phase or a topological phase, depending upon we enclose the origin, which is given by, of course, the d vector, its components dx, dy, dz, that is equal to a 0, 0, 0. Okay. So, this d vector has three components, and each of these components depend upon these the k vector, or rather the wave vector, but which is of course, because it is a one dimensional wave vector. So, we call it a scalar. Okay. So, in fact, this not being there, that is dz equal to 0, gives rise to the topological properties. Just one small point that I need to mention here is that if dz is not equal to 0, that is, if you say add a mass kind of term. Now, what I mean by that, if there is a term to go with the sigma z, then of course, all these visualizing the winding number will be a big problem, because in the dx dy dz plane, there are actually infinite number of closed loops that may include the origin or exclude the origin. So, there is no unique way of showing the winding number if all the three components are non-zero. Fortunately here the dz component is 0, and that is why the dx dy which both are functions of k, one can actually plot a closed curve that either encloses the origin, in which case it becomes a topological phase, and if it does not enclose the origin it becomes a trivial phase. Okay. So, let us see the symmetries of these SSH model. And what we mean by the symmetries is we have already discussed various symmetries that are there. So, say chiral symmetry or inversion symmetry or parity or time reversal symmetry and so on and so forth. Okay. If we talk about the chiral symmetry, so let us first talk about the chiral symmetry. Okay. And the chiral symmetry would actually mean that, so the chiral symmetry operator in this particular case is nothing but sigma z, okay, which is z component of the Pauli matrix which you see here. Okay. So, that is the chiral symmetry operator, and we need to check that whether sigma z h of k, we have already defined h of k, sigma z dagger, this is equal to what for one to have a chiral symmetry. Okay. Now, it is important to note that sigma z dagger is equal to sigma z because it is a Hermitian operator. So, we need to check what is sigma z h of k sigma z. Okay. This is equal to a sigma z, then we have a dx of k sigma x plus a dy of k sigma y, and as I said that we are fortunate not to have a dz term here. Okay. And then we will have to write a sigma z here. So, we need to check these quantities. Dx is a function of solely a function of k and is just a function, it is not matrix or an operator. So, we have to check it is a sigma z sigma x sigma z and plus a dy k sigma z sigma y sigma z, what it becomes. So, we need to calculate this and we need to calculate this. So, one way of course is to multiply 3 2 by 2 matrices that you see here, but we can do better than that. We can use the properties of this Pauli matrices, and the properties of the Pauli matrices are like this. So, this is a sigma z or say sigma x sigma z, that commutation relation is equal to, or we can write if you do matrix multiplications, then of course you need to start from the end, and this is what we are doing. So, or we can do the other way around as well. So, we just write down a sigma z sigma x commutator which is nothing but I sigma y. Okay. So, this is a known result from the properties of the Pauli matrices, and also we can write down the anti-commutation relation of sigma z and sigma x, which are of course distinct, and this is equal to 0. So, if you take both of them, so from both of them what we get is the following, that sigma z sigma x minus sigma x sigma z, this is equal to I sigma y, and sigma z sigma x from the second one, a plus sigma x sigma z is equal to 0. Okay. So, if you add both of them, this will cancel out and we get a 2 sigma z sigma x, this is equal to I sigma y, which means that sigma z sigma x is equal to I over 2 sigma y. Okay. So this is this only this part, that is sigma z sigma x, is what we have found out here, and now we have to multiply it by right multiply by a sigma z. Okay. So that's what we'll do. So we have a sigma z sigma x sigma z, this is equal to I by 2, and what we got here is I by 2 sigma y. So we'll write I by 2 sigma y and sigma z. Okay. And again we can sort of use this same technique in order to find sigma y sigma z. So sigma y sigma z, the commutation relation is equal to I sigma x. Remember that this is cyclic, these indices x, y, z are to be used in a cyclic fashion. If you break the cyclic property, then you should bring in a minus sign. And a sigma y sigma z anti-commutation is equal to 0. So this again gives a sigma y sigma z minus a sigma z sigma y, that's equal to I sigma x, and sigma y sigma z plus sigma z sigma y is equal to 0. Again we cancel these two and get a 2 sigma y sigma z is equal to I sigma x, and sigma y sigma z becomes equal to I over 2 sigma x. So if we go back to this term, the first term that we were trying to calculate, so that's dxk, so we took this term, we write consider, okay, and so this becomes equal to the first term, and let us give a name to this, let us call it as equation 1. So the first term of 1 becomes equal to, it's I by 2 into, well, there is a I by 2 that we have to take into account because this itself gave a I by 2. So I by 2 into I by 2, which have to be taken twice, and the sigma x, and of course you have a dx, a function of k. So this is nothing but a dx k, and then there is a 1 over 4 which comes from this thing, but that can be, you know, absorbed in the, that's just a constant factor, and sigma x. So you see what happens is that the term which is a dx k sigma x becomes minus dx k sigma x, okay. And similarly you can check that the second term of 1 is a dyk, and again that same thing, it's I by 2 into I by 2 sigma y. So this is equal to minus 1 by 4 dy of k and sigma y. So if you combine these two, so you have a dy of k sigma y. So I mean this becomes equal to, under this chiral symmetry operation, it becomes minus dy by k sigma y, and so on, okay. So this is the transformation of this, and so that tells you that sigma z h of k, this is equal to, and sigma z, this is equal to minus h of k, okay. So this is the chiral symmetry of the model, and this is what the chiral symmetry demands. Okay, all right. So let me see the inversion symmetry first. So this is number 2, inversion symmetry. Okay. And so inversion symmetry requires one to go from x to minus x, y to minus y and so on, okay, I mean z2 minus z. So, what I mean is that so sigma x is the operator that does that, and what I mean is by the operator is that the sigma x acting on these operators C A and C B, where A and B refer to the two sublattices that we have talked about, this becomes equal to a 0 1 1 0 C A C B. So, this becomes C B C C A. Okay. All right. So, what it tells you is that A and B sublattices are interchanged under this inversion operation, and that is what we want by the inversion operator. So, you can do this again, you can see this the sigma x h of k and the sigma x dagger, which means it is same as sigma x equal to what, and then you can see that your dx of k, that becomes a dx of minus k. So, this is what it becomes under this inversion symmetry. If you want to understand in a hand waving way, k is nothing but the momentum, which is dr dt. Since r changes sign, the k will also change sign, and that is what is shown here. And similarly, a dy of k is same as dy of minus k. Okay. So, that tells you that your sigma x h of k, sigma x is equal to h of minus k. Okay. So, this is the inversion symmetry of SSH model. All right. So, two symmetries we have worked out, and let us look at the time reversal symmetry number 3. So, the time reversal symmetry can be obtained, or rather the corresponding operator is what we call it as k, which is a complex conjugation operator. So, what it does is that it changes I to minus I and so on and so forth. Okay. So, under this you can see that your dx of k becomes equal to dx of minus k. So, what you need to look at is what is k h of k, k dagger equal to what. So, the dx component of the d vector, x component of the d vector, it sort of transforms according to this, and dy will pick up a minus sign, which is dy of minus k and so on. And so, you see then the time reversal operator, or we can call it T h of k T dagger equal to what. So, T h of k T dagger, this is equal to h of minus k, and h star of k is equal to h of minus k. Okay. So, this is h star the left hand side, and this is equal to. So, this is the symmetry that is if you take the complex conjugate of the Hamiltonian, then this becomes same as the Hamiltonian with its k reversing sign. Okay. So, these are the in short the symmetries of this SSH model, and if you really combine T and I, so we will call this by I because of the inversion, we can call this as chiral. So, let us call it as C, and this has of course a name which is T. So, if you look at a combination of I and T, so I and T leaves the Hamiltonian invariant. What I mean is basically if you combine these two symmetries, that is I and T, then both I and T, this causes the momentum to reverse its sign, but also has there is a minus sign in front of the dy because dy is complex, and it's done by the inversion operator as well as the time reversal symmetry operator. So, if you combine them, the minus sign goes away and then you get this the Hamiltonian to be invariant. So, what we have discussed so far is a simple one dimensional model with dimerization. What I mean by dimerization is that there are two different hopping, one within the unit cell and the other outside the, or rather between the unit cells, and these two hoppings are different, and as one of them becomes larger than the other, one kind of insulating state happens or occurs. And this insulating state, the nature of the insulating state rather, is determined by the winding number, which is the topological invariant. So, the winding number is finite or it's equal to 1. As you change k, there is a closed loop that forms that winds the origin. The origin is like that singularity that we have talked about earlier, and if the other condition holds, that is the inter-cell hopping is less than the intra-cell hopping, in which case this closed curve in the dx dy plane does not enclose the origin and represents a just a normal band insulator. So, this is a very important distinction between the two gapped situations. Gapped means both have a spectral gap, but however one has a winding number equal to 0, the other has a winding number non-zero which is equal to 1, and since the spectrum corresponds both of them being gapped, and the gap actually closes, or you go from one type of insulating state to the other insulating state by closing the gap at the edges of the Brillouin zone. Okay. So, now these two insulating states are definitely not identical, and that is what we are trying to say over and over again, but it is very important to realize that the topological insulator, or rather the one that winds the origin, actually houses two large edge modes, static edge modes or stationary edge modes at the edges of the system, the two edges of the system, and these are shown by calculating the probability density corresponding to the Hamiltonian, and they seem to have large weights at the edges, whereas the bulk is absolutely conducting, which means that it's the bulk states are like exponential ikx, or they are like conducting states, and at the edges one has complete insulating behavior. So, the bulk is different than the edges, makes it a topological insulator. Okay. So, we will see another model, simple model of this kind before we go to more complicated two dimensional model, and that model that we want to see now is called as a Kitaev chain. Okay. And it was sort of proposed by Kitaev, and it has it's a nice model with superconducting correlations. Okay. So, it shows topological superconductivity. What I mean by that is the states in the bulk are not superconducting, and the states at the edges are superconducting, and it's in the same spirit as earlier. The bulk behaves differently than the edges, and so it's a topological insulator. Before we go into that, let me give you, because this model actually concerns superconductivity. So, and superconductivity is not a main focus of this course. However, I just want to give a very brief overview of superconductivity. This is usually taught at the undergraduate level or even at the master's level towards the end of the solid state physics course, and sometimes it's either covered very hurriedly or sometimes not covered at all. So, it is important that this topic to be learned with interest among the students, and it is very important sort of part of solid state physics. In fact, you need to invoke the interaction between the electrons, and within a non-interacting model this phenomena cannot be understood. So, it's in the many body system the pairing occurs, and actually there are Cooper pairs that are formed. You must have heard of Cooper pairs and so on, which are paired state or bound states of electrons. Okay. This was in 1911 when Kamerlingh-Onnes, whose picture is here, he about 3 years before that this temperature has been discovered. What I mean by that is liquid helium, or rather helium was liquefied in 1908, which makes these 4 Kelvin or 4.2 Kelvin accessible to the experimentalist. I mean, it's very close to 0 Kelvin, or rather the absolute 0, just 4.2 degrees above that. And this temperature is very essential for seeing superconductivity in those days, where he took this Kamerlingh-Onnes, H. Kamerlingh-Onnes. So, he was in Leiden, Netherlands, and he was doing this experiment and so on, and then he had this ultra clean mercury, and it showed a sudden drop in the resistivity. So, this is the y axis is the resistivity. So, it was coming like this and then suddenly fell to 0 within a very small window. So, this window is really in temperature it's some 10 to the power minus 3-4 Kelvin. It just drops to 0, and he almost immediately realized that this is a new state of matter, because if it is comprising of just electrons, they would collide with each other, and if they collide with each other, that will give rise to resistance. And if the resistance is becoming 0, it becomes something like 10 to the power minus 5, which is definitely a non-measurable quantity in those days, and even now you cannot measure anything lower than that. So, if something falls to 10 to the power minus 5, we usually take that to be 0, and it happens at a temperature which is 4.2 Kelvin, and so as you reduce the temperature, you come from larger to smaller temperature, and you see that there is a sharp drop in the resistivity, and this gives rise to a new state of matter, which is called as the superconducting state. Okay. So, this is that same thing. I just wanted to show that this is just the graph, and it is a 0 resistance state, which means that the state has no resistance, which means that it has no free electrons present. If there are free electrons, then they would collide with each other, and collision of electrons would give rise to resistivity, which it is not there. So, somehow the electrons become very quiet particles, and they do not collide with each other. Now, that cannot happen. Okay. So, something must have happened to this state, and in fact, what happens is that there are Cooper pairs that are formed below this temperature, and what I mean by Cooper pairs is that it is a bound state of electrons. So, an electron with an up state in the k wave vector k, and an electron in the spin state with a minus k, they form a bound pair. And this is what was very sort of simply seen through some seminal works of Leo Cooper, who has one of the persons who has given rise to a microscopic theory of superconductivity in 1957, which was by Burdine, Cooper and Schiffer, and this is called as a BCS theory, which later won a Nobel Prize. Okay. So, the electrons below this temperature, they go into condensate, or they become a bound state, and when they become a bound state, they do not interact with each other. Okay? That is, they do not collide with each other, giving rise to a state of zero resistivity, which is what is said. Okay? Schiffer in his book has said that consider there is a room which is full of males and females who are dancing in pairs, and these Cooper pairs are like all the these males and females forming pairs and dancing, and one is completely oblivious of the other. That is, one pair does not recognize that there is another pair, so they do not collide, they do not give rise to any resistive phenomena which would have been there in presence of just electrons, that is single electrons. Okay. So, they form a bound pair, and how can they form a bound pair? That is another question which Cooper tackled, and some of the properties, before we go why it happens, there are certain properties. So, these are the metallic resistivity. You see that it sort of goes to some value here at even at 0 Kelvin. So, it does not become 0. Whereas, the superconductor at a finite temperature, which could be, say, for mercury it was 4.2 Kelvin, and then there were very large number of superconductors that are discovered, and a large number of them also obey BCS theory. But so this is the resistance is plotted versus temperature, and the first graph shows difference between a good metal and a superconductor. Okay. So, this is for a good metal, and this is for a superconductor. So, it becomes superconducting at Tc. So, this is what the zero resistivity is all about. Now, there is another interesting phenomenon, and an acid test for a superconductor. The superconductor not only can sort of lose resistivity, but it also goes into a state which is a perfect diamagnet. What I mean is that if you put a superconductor in a magnetic field, then the magnetic flux lines are pushed out of the sample, and this is the main principle behind what is called as a magnetic levitation, which would levitate a train, and the wheels of the train will not touch the rails and would be levitated because of the these flux, because of the magnetic energy that is there is a tremendous magnetic energy because of the bunching of the flux lines in the vicinity of the superconductor, and that is being shown here, that you have sort of liquid nitrogen, and you have, say, a superconductor which is kept here inside the liquid nitrogen, and there is a magnet that has been held here, and the magnet will just keep floating on the superconductor till the superconductivity exists. That is till the liquid nitrogen can support superconductivity, this will keep floating and so on. So, it happens because there are large number of flux lines that are just outside the superconductor, and this is what is shown here. So, complete expulsion of the flux lines is a property that is known as perfect diamagnetism, and this is actually shown by someone called Meissner, and I think his name is Oxenfeld. Okay. They have independently shown this, and this is also gives rise to what is called as a perfect diamagnetism. Okay. And in fact, what I mean by perfect diamagnetism is that the M by H, which is defined as a chi, which is equal to -1, and if you remember, the susceptibility of diamagnets is negative. So, usually for metals it is of the order of 10 to the power -3, 10 to the power -4 negative, I mean with the sign, negative sign, but however for superconductors it is completely cancelled, and it is equal to susceptibility is equal to -1. So, there is a best known diamagnet that one can get. So, this is the Cooper pair. So, what happens is that take an analogy of, so there is a lattice in which the lattice, you see this here, the lattice is deformed, deformed because of lattice excitations, and the electrons which are usually repulsive now mediated by these lattice excitations which are called as phonons, they start forming a bound pair, and you see a bound pair here. So, both are electrons, that is why these within the green circle you see a negative sign, and they are oppositely directed, which means one is an up spin, the other is a down spin, and they form a bound pair. In momentum space, the bound pair is formed between k up and minus k down. Okay. And we usually talk about S-wave pairing, that is the net angular momentum for the pair is equal to 0, but there could also be higher angular momentum pairing such as P wave, D wave and so on, though at least for the P wave the experimental realization is very limited. Nevertheless, we will still talk about a P wave superconductivity as we talk about Kitaev model. This picture that you see here can also be given another analogy, that suppose there is a dusty field and there is a horse running in the dusty field. So, as the horse moves through the field and you see it from distance, you do not see the horse, you see that there is a ball of dust which is migrating, okay, or which is being, which is moving in one particular direction. So, another horse will not see this horse, but will see a dust of cloud. Okay. So, exactly in the same spirit, because of these lattice excitations and because of these phonons, one electron sees the other electron not as an electron, but as a positive cloud, which is picked up by the the motion of the electron, and the positive charges are picked up around it. And that is why one electron gets attracted towards the other electron, which now is engulfed by a positive charge. So, it sees it as a positive charge and get attracted to it and forms a bound pair. You could ask the same question, that why does not this first electron see the other electron, that is the second electron, as a cloud? That will happen, but that will happen at a time scale which is much larger. Okay. So, this electron actually sees a positive cloud will happen at a much lower time scale, and that is why the Cooper pairing is formed. And there are various sort of support for this pairing scenario, and people have gone ahead and calculated what is called TC, the transition temperature at which this happens. So, this Tc is the transition temperature at which the resistivity vanishes and so on. And I mean, unfortunately, we will not talk about a k up and a k down minus k down kind of pairing, which is called as a S-wave pairing. But here let us write it in real space, and we will talk about pairing between up electrons and down electrons and so on. Okay. So, it's and these are called as the P wave pairing, and the Kitaev chain consists of a P wave superconductor. Okay. So, superconductor with P wave pairing. Let me give you preliminaries before we do calculations on this. So, this is the schematic picture of so this blue thing that you see here, the wire, it is a semiconducting wire. Okay, or it has conducting properties like a tight binding chain, and this green base that you see is actually a P wave superconductor. And so, these tight binding chain or the semiconducting chain picks up these because it is in the vicinity, it picks up the P wave superconducting correlations. Okay. Just one or two words on what we want to show is that usually C L dagger, C M dagger, C P C Q is a form of the interaction where L M P Q can be real space indices or maybe momentum indices and so on. So, this is the interaction term, and there is a Coulomb interaction with some some V0 and things like that, which depends on either momentum or position and so on. So, this is a 4 particle operator, and from whatever little we have discussed about the tight binding model or the second quantized notation, the kinetic energy is a single particle operator which looks like CK dagger CK, okay, with some epsilon k here and so on so forth. And there could be a spin which is not included here, but then you have to sum over spin and so on. So, this is a kinetic energy, or we can write it in real space as say for example Tij Ci dagger Cj, okay, and I and j are nearest neighbors. Now, you see that this is a 2 electron problem and there is a 4 electrons. So, 2 electron and 4 electrons, and this is what creates a problem, because you cannot write it in the form of a matrix, because one term contains 4 particle operators and the other term contains 2 particle operators. So, there is no common basis for one to represent both the terms within the same formalism. But a solution of that is that you do a mean field decoupling. What is a mean field decoupling? It is like saying that what is the average field felt by a student in the class of many other students. The student under consideration can have different interactions with different people, but then we disregard that there is any difference in interaction. We replace the entire student excepting him or her by all other students, and this is the essence of mean field theory. And in the mean field theory, what we do is we calculate these CL dagger, CM dagger, we calculate the expectation of this and leave these as operators. So, now when you take the expectation, it becomes a number, or you do a CL dagger, CM dagger and a CP CQ. Okay. So, you take the average values or expectation values of these things, which are the expectation values taken with respect to the ground state of the Hamiltonian. Now, these are if they are numbers, then let us call them as some delta, which is the superconducting pairing amplitude, because there are pairs that are being considered. So, a dagger and a dagger means there are 2 particles, the correlator of 2 particles being generated into the system, because CL dagger, CM dagger acting on a vacuum would give rise to 2 particles at L and M. L and M could be site indices, could be momentum indices and so on and so forth. So, these is called delta, which is the superconducting gap, and this is called as a delta star, which is the complex conjugate of that. So, now we are left with operators which are CP, CQ and CL dagger, CM dagger, okay, or you can simply write it as a delta CP, CQ plus a Hermitian conjugate, okay. The Hermitian conjugate will be the second term, which is here. Okay, with all these considerations, we write down a chain Hamiltonian, okay, which is just like what we have talked about here. There are n sides of this chain if it is a tight binding chain, but however only for the sake of simplicity we only consider 2 sides of this Kitaev chain, okay, and this is a 2-side Hamiltonian. This is the chemical potential corresponding to site 1, let us call this a site 1 and call this a site 2. This is the chemical potential for site 2, both are same in this particular case, and there is a kinetic energy which allows the electron to hop from 1 to 2. So, we are taking when I say semiconducting wire or a tight binding chain, we implicitly assume that there are electrons being present. So, this is the kinetic energy of the electrons, and this is the important one, which is the superconducting term. this is the kinetic energy, and this is the chemical potential, which fixes the number of particles. So, mu is the chemical potential and T is the hopping term, etc. Delta is the P wave superconducting order parameter. Okay. As I said earlier, that P wave superconductivity is not very common in nature, in fact very uncommon. Probably there is just one realization of P wave pairing, but however, for the sake of studying an interesting model which gives rise to topological properties, we assume a P wave correlation. In fact, it could be a S wave superconductor, which is much more commonly available in nature, but that requires more terms to be considered, such as the spin orbit coupling and various other things. I mean, magnetic field and other things. Okay. So, we are talking about a P wave pairing. This is a P wave superconducting term. This is the amplitude, or this called as a gap function. Okay. So, this is a gap function and this is kinetic energy and then the chemical potential, and I have just taken two sides of that tight binding chain. In general, there are n sides, but let us just do the two side problem. The Hamiltonian, if you write it in this basis, now this is slightly different than what we have considered earlier. There is a C1 dagger C1 and a C2 dagger C2. So, both dagger and undaggered things are here, and in general we are familiar in writing with C1 dagger, C2 dagger, etc., etc. But however, this is to bring out. So, this is a particle degree of freedom, and annihilation is related to whole degree of freedom. So, the Hamiltonian can be written in the particle hole basis. Okay, which is like this, and because the number of entries in the basis is 4. So, we have a 4 by 4 matrix where minus mu, plus mu and minus mu and plus mu are there in the diagonal elements, because you see that it is C1 dagger C1 and C2 dagger C2. So, if you write down all these things the way we have written it down here, then you get this 4 by 4 matrix, and which had, it is a spar matrix. I mean, the sum elements which is equal to 0, but then there are all these elements that are non-zero. I mean, this block, none of the blocks is equal to 0, even though some of the terms vanish. Okay, you can just write it down. It's so easy to write down. And then what you can do is that you can write down a slightly new notation in which because you are creating a particle, so you can write it as 1 electron, E for electron, and 1 stands for the site, and when it is annihilating you can write it as 1 H. C2 dagger will be 2 E and C2 will be 2 H. So, now instead of writing it C1 dagger C1, C2 dagger C2, we can write in terms of these the basis, which is 1 E, 2 E, 2 H, etc., etc., and E and H refer to the electron and the hole states. Okay. So, let me stop with stating only the two site Hamiltonian, because it will require time to sink in these ideas that we are writing down a two site Hamiltonian. So, now we have written it as 1 electron these Kets and Bras, and there is a 1 hole, there is a 2 electron, 2 hole, and then there is a 1 electron, 2 electron, 1 hole, 2 hole, 1 electron, 2 hole, and 2 electron, 1 hole. So, that kind of a basis, and nevertheless you can also diagonalize this Hamiltonian, and this Hamiltonian gives rise to the eigenvalues which are given by these 4 eigenvalues, which are T divided T plus square root of delta square plus mu square, t minus delta square square root of delta square plus mu square minus of t minus this, that is this one here with a minus sign and this one here with a minus sign here. Okay. So, these are the 4 eigenvalues lambda 1, lambda 2, lambda 3, lambda 4, and corresponding to that the 4 column eigenvectors can be found out. So, this is what we have done. These are that is an element, that is an element, that is an element, and that is an element. So, it is a 4 column vector, 4 element column vector, and there are 4 of them corresponding to the 4 eigenvalues. We are going to generalize this to n sites, and we will see that we will see the topological properties of this model and how the concept of Majorana fermions emerge from here. A concept that was originally proposed in the high energy physics, but could never be realized in nature, whereas we actually see that there are Majorana fermions, which are nothing but the particles which are their own conjugates are called as a Majorana fermions. Okay. Majorana is a name of a scientist who has proposed this, and we will see Majorana fermions, and we will further talk about the properties of this, the topological properties of this model. Again, try to write it down in terms of a d dot sigma, so that the winding can be defined and one can actually look at the how in the dx dy plane the loop encloses the origin or it does not enclose the origin, which will decide that whether this has topological features or not. And these are 0 energy modes, just like we have seen 0 energy modes in the SSH model. These Majorana fermions will be the 0 energy modes, and which can, because of their property that the particle is same as its conjugate, they cannot be separated. So, you cannot split a Majorana fermion and make them separate. So, if you at all do anything, you can shift them up from the 0 energy by giving an additional energy, but you can't separate them. And the whole idea that these Majoranas are really formed at 2 ends of the chain, that is the 2 edge modes that are the static edge modes of the system, and in principle they are they can be infinitely far away depending on the length of the chain. Now, if these 2 are so correlated, so much so correlated, that means the whole idea is that whether they can be used for any quantum information, processing of quantum information or quantum computation, because they are far away yet they are correlated, which means that if you know that in one end they are there, they will also be there in the other end. Okay. So, we will see that in the following lecture, which will be totally on this n site Kitaev chain, and this is the second paradigmatic model for topology. Okay. We will stop here. Thank you for your attention.